Alright, welcome. My name is Ian Brown, and this is the first video in what should be an ongoing series about linear algebra. In this first video, we're going to talk about linear systems and vectors. So this is an example of a linear system. You've probably seen something like this before. Two linear equations that relate the same two variables x and y to one another. And that's our system. It's just the collection of these two equations. We have two pieces of information about x and y, and that allows us to solve for x and y simultaneously. So we should have a rigorous definition of what a linear equation is. And to do that, we first have to define something called a linear combination. So if I have a set of something, I could have a set of functions, but in this case, we'll say that I have a set of unknowns or a set of variables, x1, x2, all the way to xn, so I have n of them and they're just indexed by the subscript. Then a linear combination of those unknowns is where I take each one of them, I multiply them by a respective coefficient a1, a2, all the way to an, and then I take the sum of all of those terms. And what a linear equation is it's just where I take a linear combination of variables and I set it equal to a constant, which is b in this case. So here's an example of a linear equation written in this form. So I have a linear combination of x, y, and z. X has a coefficient of 2, y has a coefficient of 0. In this case, we just wouldn't write the y term, but if I didn't, then it's implied that the coefficient is 0, and z has a coefficient of -1, and those are equal to the constant 4. So here's a larger, more complicated system. I have 3 unknowns and 3 equations, and I can write this system as a matrix, which for now, it's best to think of as just a better notation for a system. Instead of writing the coefficients and the associated unknowns and then addition and, writing it as a whole equation basically, I just write an array of the coefficients for all of my unknowns and all of my 3 equations on the left side, and on the right side, I write the constants that they're equal to. So you can see each of the rows in this matrix corresponds to an equation, and each column corresponds to the coefficients of some variable. The first column corresponds to the coefficients of x, the second, the coefficients of y, the third, the coefficients of z, and that fourth column on the other side of the vertical rule just represents the constants in our equations. So here's that same system, and we're going to use a process called Gaussian elimination to solve the system. What does that mean? Well, when we solve a system, we're just finding the values of our unknowns that make the equations of the system true. The equations of the system are pieces of information, and we just want to use them to simultaneously find the values of our unknowns. To do this, Gaussian elimination is going to take our matrix to a form called a row echelon form, which I might abbreviate REF. And what that looks like is basically I have something in my matrix called the main diagonal, which is the sequence of terms from the upper left to the bottom right. To begin with, our matrix has a main diagonal 3, 0, -2. And a row echelon form involves making all of the entries below the main diagonal, which to begin with are the terms 1, 0, and 2, and it makes all of those entries 0. Then, all of our terms that are non-zero on the main diagonal, and they could be 0, but those which are non-zero need to be made into 1s. And the rest of the terms of the matrix can be anything. So we're going to accomplish this with 3 operations, which are called row operations, and I have them here: row swapping, row scaling, and row combination, and let's go over each of those now. So row swapping is pretty straightforward. If our matrix is just a notation for the system, and the system is just a collection, a list, if you will, of our equations, then there's no reason why I can't simply change the order of their equations. A purely cosmetic operation, really. I just might want to write the equations in a different order for reasons of clarity. Row scaling is something else I can do. I have an equation, I can multiply the entire thing, left side and right side, by some common multiple. I should probably explain this abbreviated notation here. In the previous slide, when I say r sub 1 swapped with r sub 2, it just means that I'm taking row 1 and switching it with the position of row 2. Here, this means I'm multiplying row 2 by a factor of 2. And finally, we have row combination. This means that I'm adding 1 of row 1 to row 3. Essentially, I'm taking all of the entries of row 3 because the second row that I write in this abbreviation of my operation is the one that gets altered. I'm taking all of my entries of row 3 and I'm adding to them the corresponding entries of row 1. And why is this a valid operation to do? Well, if an equation is just a statement that two things are equal to each other, then by adding one equation to another, I'm just adding two things that are equal to each other to two things that are equal to each other. In other words, the left side of one to the left side of the other, and the right side of one to the right side of the other. So now we're going to use this system, this matrix, as an example and actually perform Gaussian elimination on it. So the first thing I like to do before I get into the actual procedures is I like to reorder my rows that begin with non-zero entries that have non-zero leading entries, and I like to order them in the order of ascending leading entry. So I swapped row 1 with row 2 because row 2 initially began with 1 and row 1 initially began with 3. I want to swap them so that the row that begins with 1 comes first and then the row that begins with 3, and if I had more rows that began with non-zero entries, then I would order them like that, so on, and then all the rows that begin with 0 come after that. So you'll recall that to get this matrix to row echelon form, I need to make all of the entries under the main diagonal 0. So to start with, let's just focus on the first column of the matrix. The term at the top is already a 1, so not only is it non-zero, but it's also a 1 on the main diagonal. So that term is going to remain how it is throughout the entirety of this process. It happens to be good to begin with. And you'll see I do have 1 0 in that column, so that is 1 0 under the main diagonal, but above it is a 3, and I don't want that 3 to be there. I want to eliminate it. I want to make it 0. To do this, I can add -3 of row 1 to row 2. And how does that do that? Well, -3 of row 1 means that for the first entries, for the entries corresponding to x of rows 1 and 2, I'm taking -3 of row 1, so that's -3 times 1, the first entry, added to the first entry of row 2, which is a 3. So -3 plus 3 is 0. So in other words, to eliminate the entries under the main diagonal to make them 0, I have to use the leading non-zero entries of the rows above, multiply them by some factor, and then add them so that when those non-zero leading entries are added to those below them, they make the entries below them 0. So -3 of row 1 added to row 2 eliminates the first entry of row 2, and of course I alter the remaining entries of row 2 accordingly. I take all of those entries of row 2 that remain and I add -3 of the corresponding row 1 entries to them. Then all that remains is one non-zero entry under the main diagonal. It's that 2 under the -1. So that -1 that leads in the second row, at least for the non-zero entries now, I can multiply that -1 by 2, meaning that of course I have to multiply the whole row by 2, and then I can add that row to row 3, and you'll see that -1 times 2 is 2, and -2 added to 2 makes the 2 below it a 0, and now all of my entries under the main diagonal are zeros. This form is called an upper triangular matrix. It's not quite in row echelon form because the main diagonal has to be comprised of 1s or 0s, but it is an upper triangular matrix because all of the entries under the main diagonal are 0s. To take it to row echelon form, I simply multiply rows 2 and 3 by whatever factors I need to make those leading entries 1s. Row 1 doesn't have this problem, so I don't have to deal with it. If I multiply row 2 by -1, that becomes a 1, and if I multiply row 3 by 1/6, then its leading non-zero entry also becomes a 1. And you'll notice throughout the entirety of this process, I was changing the constants on the right side as well. So don't forget the operations apply to the left and right sides of the matrix, the coefficients and the constants. So now I have this matrix in row echelon form, and technically this is good enough to solve. What does that third row say? It's an equation where I have isolated z. It's an equation only in z, right? So when I have an upper triangular matrix, the reason why it's such a useful and desirable form of the matrix is that I usually will just have an equation in one variable. So that third row says that 1z, or simply z, is equal to -7/3. I can substitute that value of z back into the above row and solve for y. That's called back substitution. So if y minus 4z equals 7, then y equals 7 plus 4z, and then if I substitute -7/3 in for z, I solve for y. Y happens to be the same thing, and then I can take my values of y and z and substitute them back into the very top row, and then I can solve for x, and that's negative 1/3. However, this isn't the best way to do it. Okay, generally it's not good to solve our system by taking it to a matrix and doing row operations and things with matrices just to convert it back to a system that still requires work. Instead, we're going to continue with the process. At the top here, I just have the row echelon form matrix, and I'm going to continue the process with something that's now called Gauss-Jordan reduction, and you'll see this takes the matrix to a much better form called reduced row echelon form. So, to take the matrix to reduced row echelon form, I now just have to eliminate all of the entries that are above the main diagonal, if I can. So, the first thing I have to do is I have to eliminate that -4 in the third position of row 2. To do that, I can just add 4 of row 2 to row 3. You'll see how that works. The 1 that is below the -4, when I multiply it by 4, it becomes a 4, and then when I add that 4 to the -4 above it, then that -4 entry becomes a 0. So to eliminate the -1 in that top position now, I just add row 3 to row 1, and you'll see that eliminates the top right entry. And this is the row echelon form. I mean, that is it. You'll notice this matrix is so great because it's even better than an upper triangular matrix or a row echelon form matrix where we can do back substitution, because this explicitly tells us the values of x, y, and z. All of these rows translate perfectly to equations just in one variable. So here's another example of a system. This is a rectangular matrix. I suppose a square matrix is also rectangular, but I mean explicitly non-square. And of course, this would correspond to the system written in equation form as x minus y plus z equals 0, and 2x plus z equals -1. Of course, that middle term just means plus 0y. So to take this to row echelon form, well, first I should say that the main diagonal is not a concept that's entirely applicable to non-square matrices, but in this case, we think of the main diagonal as being the upper left entry, and then, so the first entry of row 1, and then the second entry of row 2. So to begin with, in this beginning matrix, I can use my cursor here. This 1 and this 0 constitute the main diagonal. And then the sole term that's under the main diagonal is this 2. To make it a 0, I multiply row 1 by -2 and add it to row 2. And this term is a 0. Okay, now to get this to row echelon form, I just multiply row 2 by a factor of 1/2 to make this entry in the main diagonal a 1. And this is the row echelon form. It's great, it only takes 2 steps. Then, to take it to reduced row echelon form, which I've abbreviated RREF, I just have to do one more step. You'll notice to eliminate the sole term above the main diagonal, which is this -1, I have to just add row 2 to row 1. So this 0 and this -1 that remain here, these are technically not above or below the main diagonal. They aren't really relevant for reduced row echelon form because we can't affect them with row operations. We can only affect what is below, above, or on this main diagonal, but to the side here, we don't have a third row that goes below it, so we just can't do anything to these. Alright, so this is a pretty interesting result that we're left with. The first equation is pretty straightforward, x equals -1/2. But the second equation says that y minus z equals -1/2, or y equals -1/2 plus z. And z, well, z doesn't actually have an equation of its own. So in this case, we have more unknowns than we have equations. And you can perhaps intuitively understand that if I have more unknowns than equations, then I'm really limited in the information I have to solve for these variables. I have a bunch of unknowns, but fewer equations than them. Generally, the good, normal case is having as many unknowns and as many equations as each other. But in this case, because we have fewer equations, fewer pieces of information about more variables, you can imagine that our result will be less constrained. We won't have a unique solution like we did in the last example. In this case, we will have many solutions that depend on the value of z, and that's true. So in this case, since z doesn't have an equation of its own, we just say that z is equal to itself, y is equal to -1/2 plus z, and x is equal to -1/2 plus 0z. So x and y can actually both be written in terms of z. Even x, like I said, you just would say plus 0z. And that's what makes x and y the pivot variables. We can either solve for them directly or solve for them in terms of z. But z is the free variable because it is not expressed in terms of anything else. It is only equal to itself, and it's free to vary. That's what the term free implies. Whatever value it assumes, in effect, determines the values of x and y, and thus determines the values of the whole solution. Okay, this is another example of a system. This is a homogeneous system, which is a system where all of the equations are equal to 0. So the constants on the right side are all zeros. And because of that, you can imagine that in our row operations, the constant column on the right side won't be affected. It just won't change, because any operation that I do, it's a row scaling, row swapping, row combining, it will affect the left side with the coefficients. For the right side, I'll just be scaling zeros, or I'll be adding zeros to each other, or swapping zeros. And so nothing about the right side will change during our row operations, so I can just only write the coefficient side of the matrix when I do row operations to a homogeneous system. Okay, so here it is at the top. The operations happen to be quite numerous, but the point I was trying to make here is that you can only write the coefficients for a homogeneous system. We take it to row echelon form, and then we take it to reduced row echelon form. And this is what it looks like. It's a main diagonal of ones, zeros below and above, and on the right side we have those zeros that it's equal to. They're just implied that they're there. So this says x equals 0, y equals 0, and z equals 0. So they're all equal to the same thing. And this is a special kind of homogeneous system. We're about to give an example of the other one, but let me just go back for a moment. So this kind of homogeneous system is called a non-singular homogeneous system, or a non-singular matrix. And I'll talk more about that later, but basically you can identify a non-singular matrix as the matrix of coefficients for a homogeneous system that is square, and its reduced row echelon form will always have this form of ones completely down the main diagonal. There will be no zeros on the main diagonal, and that's why it's non-singular. That is opposed to, of course, a singular matrix, which is another kind of homogeneous coefficient matrix, again for a square homogeneous system. And you'll see that when we take it to reduced row echelon form, or row echelon form first, right, and then reduced row echelon form, we do not have ones completely down the main diagonal. We actually have a 0 on the main diagonal, and that's the first time we've seen this. And why don't I go back for a moment and see if you noticed something about this matrix that we started with. One of the rows is a multiple of the other. This second row and this third row, they're multiples of each other. The third row is the second row multiplied by -1. And so if you ever have a matrix, specifically a square matrix, right, and we can imagine that that's the matrix of coefficients for a homogeneous system, then if one row is the multiple of another one, that is a good way to immediately identify it as a singular matrix. In this case, this example was chosen for that reason. And these are just the steps of Gaussian elimination. I'm just, again, eliminating the terms under the main diagonal, making them 0, and then this is what I'm left with. And then I just simply add row 2 to row 1, and it's in reduced row echelon form. In this case, I could not eliminate one of the terms that was above the main diagonal, which is this -1. And that's okay. Essentially, reduced row echelon form is going to be eliminating all of the terms above the main diagonal that you can. So terms above the main diagonal that are above zeros on the main diagonal will not be able to be eliminated. And when we solve for our variables, you'll see x is equal to 0. That's what the first row implies. Y is equal to z because y minus z equals 0. And this third row says that 0z equals 0. Well, if 0z equals 0, 0 of any number equals 0, doesn't it? So z could be any real number. So z can be any real number, y is whatever z is, and x is, regardless of these two, always 0 itself. Okay, so to continue talking about systems and matrices, I'm going to have to take a detour to talk about vectors first. We write vectors as columns. You may have written them as sort of ordered pairs with angular brackets before, but we're writing them as columns now, and we call them column vectors. So you can have vectors. They're essentially ordered lists of numbers of any size. This is a 2-dimensional vector because it has 2 entries. This is a 3-dimensional vector because it has 3 entries. And this is an n-dimensional vector with arbitrary n number of entries. So vectors, of course, can be represented visually, graphically, if you will. Let's say that 2-dimensional vector A was 3, 2. So those are its components. So what this means is that A is an arrow in space that corresponds to traveling a distance of 3 in the x direction and then 2 in the y direction. And this vector in particular is drawn in standard position because it starts from the origin and ends at the point that has the coordinates of the vector's components. But a vector can start anywhere in space. I could start this vector at the point 1, 1, which would be about right here. And in that case, this vector would end at the point 4, 3, because from the point 1, 1, it would travel a distance of 3 along the x-axis and then 2 along the y-axis. So a vector just describes a step that you can take in space. So vectors can be added to one another, and they can also be scalar multiplied. So when we add vectors, we just add the corresponding components. So the x components are added together and the y components are added together for this vector. And we can also scalar multiply them. So if I take a vector and multiply it by a scalar r, then I'm just multiplying both of the components by that scalar r. So here's an example. I have two 4-dimensional vectors, and when I add these two vectors, I just add the corresponding components, right? How did I get this first entry, -1? I said 1 plus -2, and that's -1. 2 plus 0 is 2, 3 plus 1 is 4, 4 plus 3 is 7, and that's how I did this vector addition. I could also do addition and scalar multiplication together. So the first thing I do is I deal with this term with the scalar multiple. I take the vector 1, 2 and multiply it by 5. So then it becomes the vector 5, 10. And then I add 4 and -3 to 5 and 10, and I get 9 and 7. So of course, vector addition and scalar multiplication can be represented graphically. So if I take two vectors in space, or in two-dimensional space, and I add them together, a good way to phrase it that it's often said is you add vectors tip to tail, meaning that if I draw a vector in the standard position, this first blue one, 4, 1, then I add the vector -2, 3 to it, I first draw the vector 4, 1, and then I draw onto its tip the vector -2, 3, the red vector. And this path that we've taken, first along the blue vector and then along the red vector, describes a new path, this purple vector, which is their sum. Scalar multiplication is even more straightforward. You just take a vector and scale its length by the scalar. So the vector 3, 2 multiplied by a scalar of 2 becomes the vector 6, 4. It just lengthens by a factor of 2. Okay, so now I will ask you to recall the first example of a matrix. This was that matrix, that first one in reduced row echelon form. And we can write our solution as a vector. There's no reason not to, and there are many reasons to do so. You'll see that the sets of solutions can be described very nicely when we use vectors. So I use these open curly braces here and then put my solutions inside because the curly braces denote that this is my set of solutions. In this case, the system has a single unique solution. My solution set consists of one vector where the components correspond to the values of x, y, and z that solve the system. Here's the rectangular example. Again, this was the reduced row echelon form. And the solution set is a bit more complicated. Why don't I explain? So I have two vectors here. I have a constant vector, and then I have a vector multiplied by z. And you'll recall that z was the free variable, right? And x and y were the pivot variables. X and y were either written, solved for directly or in terms of z, and z didn't have an equation of its own in this system because there were more unknowns than equations, and so z was just equal to itself. So x is equal to a certain constant part plus a certain number of z's, and y, because it's also a pivot variable, is equal to a certain constant part plus a certain number of z's, right? Because the pivot variables are written in terms of first a constant and then plus a certain number of z's. But since x was equal to -1/2 plus 0z, the x position of the sum of these two vectors, the constant vector and the vector with the z, is just going to be -1/2 always. So x is always -1/2. Why? Y could be -1/2 if z were 0, but y is generally a lot of things. Y is generally -1/2 plus 1 times however many z's we have. And z is just equal to itself. Z is equal to 0 because there's no constant part, plus 1 of itself, plus 1z. And so in this case, we say that this is a solution set with infinitely many entries, infinitely many vectors in the solution. Z parameterizes the solution set, meaning any value of z describes a specific solution with a specific vector that we get from adding these two after we decide on a specific value of z. And you'll notice that the components of that vector give us exactly the values of x, y, and z that solve the system for that particular value of z that we choose. This just means that z is a member of the set of real numbers, so z is any real number. It could be 5, -17, 4,000. It's just some real number, but whatever real number value it assumes determines the values of x and y. Okay, so this was our homogeneous non-singular example. I didn't call it non-singular earlier, but this is just opposed to the singular example of a homogeneous matrix, which came after. So this was the reduced row echelon form, and here's our solution set. So you'll recall, because I said that this was a non-singular matrix, I had ones all along the main diagonal. And because I have ones all along the main diagonal, and the constant column is 0, this means that I can solve for all of my unknowns directly. There will be no free variables. They're all just directly in some constant rather than being in terms of one another. And that's something that you'll notice whenever I have a main diagonal of entirely ones after taking it to reduced row echelon form, regardless of what the constant column is, right? It doesn't have to be a homogeneous system, but whenever I have a main diagonal of entirely ones, I will always have a unique solution rather than having to solve in terms of a free variable. That is, of course, only if the matrix is square. So a homogeneous system where we have ones all along the main diagonal is a homogeneous system that is non-singular, where we can solve for all of the variables directly. And since it's homogeneous, our solution set consists of only one vector. And this is a special vector called the zero vector. So you might just write it as a 0 with the vector arrow over it because it's a pretty important vector. And when our solution set consists of just the 0 vector, then that's called the trivial solution. Non-singular matrix has only the trivial solution. Okay, here's the singular homogeneous example. This is the reduced row echelon form again with and without the constant column. And its solution set is, of course, parameterized by z. Because we don't have a main diagonal of ones, we have a 0 on the main diagonal, just 1 in this case. And so because of that, we have to solve in terms of a free variable, which is z. And because of that, there are non-trivial solutions. Because of that, we can't just solve for x, y, and z directly for only one unique solution. We have multiple solutions, one of which is the trivial solution. So that's important. Whenever you have a homogeneous system, non-singular or singular, the trivial solution, the 0 vector, is always one of the solutions, but non-trivial solutions also exist. That's the definition of a singular matrix. A matrix of coefficients for a homogeneous system, which is square, where non-trivial solutions exist. If z is 0, then this the 0 vector, the trivial solution, but if z is 1, then we have a new non-trivial solution. Okay, so now I'm going to introduce a new example. Here's a system, and this is a system with 2 unknowns, but 3 equations. So now we have a different kind of imbalance, more equations than unknowns. So I'd write it as this matrix. This kind of matrix, by the way, is called an augmented matrix, where I have the coefficients on the left and the constants on the right. I don't even need to take this to row echelon form, in fact. I just need to eliminate the terms under this first column, under the 1 in this first column, and you'll notice I get, after these 2 row operations, -1 row 1 plus row 2 and row 1 plus row 3, I eliminate the 1 and the -1 here, and I have 2 equations that are only in y. And those equations are, those equations are -3y equals 2 and 5y equals -1. So when I solve for y, I get 2 conflicting values. The second row gives me y is equal to -2/3, and the third row gives me y is equal to -1/5. So these are conflicting values. And in this case, we don't think of our equations as pieces of information like we did earlier. Now we think of our equations as constraints. In other words, when I have just as many equations as I have unknowns, or fewer equations than I have unknowns, I think of each of my equations as something that is generous, if you will. Each one is helping me with information to try to find a solution, to try to find the values of x and y, or x, y, and z, and so on. But in this case, since I have more equations than unknowns, we can think of our equations as constraints, as demands that are placed on us and our variables. And what essentially we're asking is, if I have these 3 constraints, does there even exist a set of values or a pair of values for x and y that solve this system? if I place these 3 constraints down, but for only 2 variables, are there values for x and y that even make this true? And in this case, because we have 2 rows that disagree with one another, we have 2 conflicting values for y, it can't be both, it can't be either, there is no solution. So it is, in other words, impossible to solve this system. It is impossible to find values of x and y that make all 3 of these equations true at the same time. The solution set is the empty set. We might write that as just 2 empty open curly braces, or we might write it as the no solution symbol here. Okay, so I have another example here. I have 2 matrices, 2 systems, and you'll notice these are actually the same system other than the constants. They have the same coefficients on the left side, but on the right side, one of them has the constants 1 and -1, and the other one is homogeneous. So when I take the solutions of both of these, and you'll notice something interesting. The solution to the inhomogeneous system, the first one, consists of a constant vector, 0, -1, 0, which is right here, and then another vector that's multiplied by z. And for the homogeneous system, we just have a vector that's multiplied by z. And you'll notice something interesting. The homogeneous solution appears in the solution to the inhomogeneous system. This vector z times -1, 1, 1 appears right here. Z times -1, 1, 1. And it turns out that the general solution, that is the set of all solutions to an inhomogeneous system, is a particular constant vector, 0, -1, 0 in this case, plus the solution to the homogeneous system. And why does this make sense? Well, when I take both of these matrices to reduced row echelon form, they're both going to have x and y in terms of z, because I have more unknowns than I have equations. So I already know that I'm going to have a free variable in both cases. And I know, of course, that I'm going to have the same free variable in the same situation with x and y being in terms of z in both cases, because they have the same coefficient matrix right here on the left side. So they're going to reduce in the same way on the left side. But there's a difference in how they reduce on the right side. The right side of the homogeneous system will always have zeros. It won't change. That's why we can just write the coefficient matrix when we do our row operations. But the inhomogeneous system will have its right side change throughout the operations. And so when I solve for x and y in terms of z, I'm going to have to include a constant part for both of them, which are 0 and -1, and the parts that are in terms of z. When I take these solutions, when I take the values for x and y in terms of z in the homogeneous system, there cannot be a constant part. For the inhomogeneous case would equal a constant plus some number of z, and y would equal another constant plus another number of z's. But in the homogeneous case, those constants have to be 0, right? Because the only place we could get constants is from the right side, but they're going to be 0 the whole way through. So when I solve for x and y in terms of z, I just get that x is equal to some number of z, and y is equal to some number of z without any constants added. I have these particular constants for the general solution to the inhomogeneous one, and this constant vector is called a particular solution to the inhomogeneous system, because if I take z to be 0, then the solution to this system here is just going to be 0, -1, 0, right? Because z is 0, so this vector is eliminated. And so it's a particular solution to the inhomogeneous system, and the reason why it is particular to just this system is because the constants in this first vector of the solution are determined by the constants that I have on the right side here. When I want to find the general solution to an inhomogeneous system, sometimes if I know a particular solution or if I can find it easily, it's best just to not solve the whole inhomogeneous system, but to solve the homogeneous one, so I can find this homogeneous part, which is the z times -1, 1, 1. And then if I know the particular solution, I just add the particular solution to the homogeneous one that I found. And finding the homogeneous solution is always easier because we don't have to worry about the constants. So that's why it's preferable. And that's my general solution to the inhomogeneous system. General equals particular plus homogeneous. Okay, so now that we've described solutions, I want to think about linear systems once again. So here is a linear system. I have indexed the coefficients with this subscript here. The subscripts, the first number just indicates the row and the second indicates the column. So if this is A23, and what that means is that it's in the second row and the third column, which we can see. So what is the meaning of this? Well, x, y, and z are the values that solve this system, that make it true. right? And then b1, b2, and b3 are just constants. So if x, y, and z are the values that solve it, then x, y, and z in a vector are the solution. We've already seen how to describe the solutions as vectors. And so it seems like when I take my vector of solutions, whether it's a unique solution or a set of many vectors, and I put it into my coefficient matrix, which is this is the coefficient matrix for this system, it gives me constants. It seems like I could actually write this system, which I originally had in its equation form here, as a linear combination of vectors. I mean, let's think about this for a moment, okay? What is this first row saying? It's saying x times a11 plus y times a12 plus z times a13 is equal to the constant b1. And really, all of these rows that we would get, all of these equations that we would get from this linear combination of vectors produces exactly the equations that we had in this system right here. And this is the definition of the matrix vector product. We're applying this matrix to this vector. And again, the way that that works is we take the first entry of our vector, which we don't know, that's why it's a vector of unknowns, and we multiply it by the first column vector of this coefficient matrix. And then to that we add the second entry of the vector of unknowns multiplied by the second column vector of the coefficient matrix. And then to that we add the third entry of the vector of unknowns and multiply that by the third column vector of the coefficient matrix. And the linear combination of the column vectors of this matrix multiplied by the coefficients, which in this case the unknowns serve as, is equal to this specific constant vector. And so when we're solving a system, what we are really asking is what vector of unknowns, when this matrix is applied to it, or in other words, what vector of unknowns whose entries serve as the coefficients for a linear combination of the column vectors of this matrix here, produces this specific constant vector. Okay, so this was the first augmented matrix in the first example, and this is how we would write it in this matrix vector product notation. Our vector of unknowns is having this matrix of coefficients, which is the same as the coefficient side of this augmented matrix, applied to it, and that equals this vector of constants. So in that case, we ask what vector, when this coefficient matrix is applied to it, yields this vector of constants. And this is the sort of expansion of that. In more abstract terms, with sort of arbitrary n-sized matrices and vectors, we see that we have this coefficient matrix A. Again, the first number of the subscript is the row, the second entry of the subscript is the column. Okay, this is just an n by n square matrix of coefficients, and I have a vector of length n, an n-dimensional vector, and this is the matrix vector product, the linear combination of the columns of A, where the entries of x are the coefficients. Each row obviously corresponds to a linear combination of the unknowns, where the entries of the coefficient matrix are the coefficients. So it's either multiple linear combinations of the unknowns or one linear combination of the column vectors of the matrix. And another thing that you might notice is that for this matrix vector product to exist, we need to have as many entries in this vector as we have columns of A. But that should make sense, shouldn't it? If I have a linear system, I need to make sure that that linear system, just in its equation form, accounts for all of the unknowns that I'm asking about. If I have 4 unknowns, say x, y, z, and w, then I need to make sure that every equation has a term for each of those unknowns. And let's say my second equation has no w term. I could still interpret that as plus 0w, for example, but in that case, the entry in the second row for the w position of the coefficient matrix would just have 0, but every unknown from the vector of unknowns here, which is x, has to be accounted for by the matrix. So you can almost think of turning this vector on its side and then distributing the unknown to each of the columns of this matrix, and that yields our specific equations. Okay, so now that we have these two different ways of interpreting systems, we can go with that further and also perhaps look at it from a geometric point of view. So here's a linear system, just in equation form. Here's the solution set. There is a single unique solution. X is equal to 4, y is equal to 7. So this blue equation and this red equation are just the equations of the linear system. And of course, linear equations can be graphed. In 3D space, we would have planes. In 4-dimensional space, we would have some 4-dimensional equivalent of something linear, but in 2-dimensional space, we have lines. And since the values that solve this system are, in other words, common between these two equations and are the sole common x and y values between these two equations, then we can imagine graphing the blue equation as a line and the red equation as a line, and the points where they intersect will be the solutions, and they intersect at one point, so they have a unique solution, and of course that point has the coordinates 4, 7, the x value 4 and the y value 7, which was the only solution to the system. So if I graph the rows of my linear system as lines or planes or so on, then their intersection point or their intersection points will be the solution. So if there is one intersection point, there is a unique solution, and the coordinates of that point are the values for x, y, and so on. If they intersect at infinitely many points, then we have infinitely many solutions, and if the lines are parallel, or we have planes in space that just don't intersect, then there would be no solution because there are no common x and y values or x, y, and z values between the graphs of the rows. Right? We can also look at this system from the perspective of the columns. Right, here is the system in the form of the coefficient matrix, which is this matrix 2, -1, -3, 2, applied to the vector of unknowns, and that equals this constant vector. And in the middle here, we just have the expanded matrix vector product, where it's x times the first column, 2, -3, plus y times the second column, -1, 2, and that's what we have here. And so now, when we're trying to find x and y, what we're really asking is, I have my two column vectors of the system, and x is how many vectors 2, -3 I have, and y is how many vectors -1, 2 I have. And basically what I'm saying is, how many of the first vector plus how many of the second vector, -1, 2, is equal to this constant vector? How many of this plus how many of this equals this? And in this case, there's one unique way to do that, and it's when we add 4 of the first vector and 7 of the second vector. When we add these vectors tip to tail in a visual and geometric sense, we get this black vector, and it's the only way to get this black vector. And that black vector is 1, 2, which is the constant vector that we were aiming to produce by taking this matrix vector product. Finally, I just want to reiterate this key equation here. A times x is equal to b, where a is the matrix, the coefficient matrix, x is the solution vector or the vector of unknowns, could be x1 to xn, could be xy or xyz, and b is the vector of constants. I either have a linear system thought of as a collection or list of equations where the entries of a are the coefficients that describe some linear combinations of our unknowns equaling a bunch of different constants, or I think about this as a single linear combination of the column vectors of matrix A, where the coefficients are now the entries of vector x. And that linear combination of vectors is equal to 1, which is the vector of constants b. Alright, so that is the end. That's the first video. I commend you for watching it to the end and for taking an interest in linear algebra. And if you're interested in more of these videos, then stay tuned because I will be releasing another one shortly.